Hello everyone, and welcome to the Law of Universal Gravitation post-lab. It's kind of a long post-lab as we had 3 parts to the lab and then we have to put them all together into one big math model. So part 1 was really looking at direction, getting a feel for what happens when you are different distances away, right? And the next part here, which is part 2, is where we actually started the lab portion of it. In this case, we varied mass 1, one of the 2 masses, and we measured the resulting force of gravity. Mass 1 in kilograms, force of gravity in newtons. And we got a beautiful linear graph that went through 0, 0, which tells us, hopefully not so surprisingly, that the force of gravity is proportional to mass 1. After all, this is what we found in the lab we did with the spring scale in the room earlier, right? That the force of gravity depends on the mass of the object. So let's make a math model out of this. Right? The y variable is, of course, the force of gravity. The slope, if we take a look at the slopes, right, we see that they're all very similar to one another. I mean, it should be, after all, it's a simulation. It's a small number, which is what makes this lab kind of hard to do in reality, right, as opposed to using the simulation. It's 1.34 times 10 to the negative 9th. So if we drop that in, units of rise over run, so newtons per kilogram. Yes, we can reduce these, but in this lab, I want to leave them this way. The x variable is, of course, mass 1, and the y-intercept is 0, which means when there's no mass 1, there's no force of gravity. I mean, you have to have actual masses to exert forces of gravity. In this third of the lab, we kept the other mass, mass 2, constant at 500 kilograms, and the separation distance constant at 5.0 meters. Now those constants are important when we get to the next part. So here's part 3, where this time we varied the other mass to see what effect it would have on the force of gravity, and hopefully it wasn't too shocking to you that you got the exact same graph. And not only the same shape graph, a linear graph that went through 0, 0, but that means there is the same relationship here. Well, I hope it kind of makes sense. It's a Newton's third law thing, right? If M1 is pulling on M2 with a certain force of gravity, then M2 has to be pulling back on M1 with an equal size force of gravity. Equal in size, opposite in direction is a Newton's third law. Right? So if the force of gravity is proportional to changes in M1, it also better be proportional to changes in M2. Y equals mx plus b on this nice linear graph. The y is, of course, the force of gravity. The slope, hopefully by that point, not too disturbing that it ended up being exactly the same as it was last time. Right? Same slope. With the same units, newtons per kilogram. The x variable in this case is m2, and the y-intercept is again 0, 0, which means if there's no m2, then there's no force of gravity. There has to be an interaction between M1 and M2, and so they have to exist. In this third of the lab, we kept the other mass, mass 1, constant at 500 kilograms, and the separation distance constant at 5.0 meters. And that's a key thing. Notice that these are the same constants we used in the previous part. I considered having you use a different mass and a different separation distance. It wouldn't have changed the shape of the graph, but it would have given you a different slope, right? Since these do affect the force of gravity, it would have given you a different slope. But I wanted you to see kind of the Newton's third law aspect of this pop up in the data. So that's why I had you use the same constants. Now the next part of the lab, the part 4, was a little harder to linearize and to wrap your brain around, right? And that was the relationship between the force of gravity in newtons and the separation distance in meters. When you graphed it, you got a graph that looked like that. And that, of course, is a hyperbola. It means as you moved the masses further apart, as the separation distance got bigger, the force of gravity got smaller. Bigger separation distances, smaller force of gravity. And that's an inverse relationship. So your first attempt to linearize should be to invert. So 1 over the separation distance in 1 over meters. But that didn't linearize your graph. That gave you kind of a weak top-opening parabola. Probably wasn't as as curvy as mine, right? But still a top opening parabola. And as we know, to linearize a top opening parabola, you square the x. So if you graph the force of gravity in newtons versus 1 over the separation distance squared in 1 over meters squared, that should have given you a beautiful linear graph that went through 0, 0. Now be careful, this is the graph that we're going to analyze because this is the linearized graph. And since it is linear and goes through 0, 0, we can say that the force of gravity is proportional to 1 over the square of the separation distance. Or if you want to use the fancy words, the force of gravity is inversely proportional to the separation distance squared. This is our first exposure to a relationship that does pop up from time to time in physics. It's called an inverse square relationship, right? Where one variable is proportional to the inverse square of the other. It pops up in different things like in wave propagation and light and some other things in physics. And we're going to talk a bit more about this in the kind of deeper exploration we're going to go into how Newton came up with all this stuff, since he couldn't do a fancy simulation like this. Okay. Make the math model out of the linearized graph. The y variable is still the force of gravity. The slope here, still small, but not quite as small. Notice it was 1.67 times 10 to the negative fifth. Right. Now what about the units? Well, the units are rise over run. I'm going to kind of do this all at once. So it's a Newton over 1 over meter squared. But dividing by 1 over a meter squared is the same as multiplying by a meter squared over 1. So it's a Newton meter squared when it's reduced. Don't worry about what that means. We'll get to it a little bit. Okay? The x here, linearized graph, is 1 over r squared. That's what gives us this original graph. And the y-intercept is 0, but note there is no 0 on the original graph. Right? So this is kind of a calculus-y thing. In order to get as r gets bigger and bigger, right, the force of gravity gets smaller and smaller. So in a kind of a pre-calcish kind of way, right, as r approaches a really, really, really big number, like infinity, the force of gravity shrinks to 0. And this is important to realize kind of the limits, right? So if you can pull two masses infinitely far apart, they won't interact with one another. But it's got to be infinite. Even if they're just really far apart, they're still small forces of gravity. Eventually, they get so small that they're hard to measure. So a little weird again. It's that inverse relationship thing popping up. In this part of the lab, we kept the mass of both objects the same, just for simplicity's sake. Both of them were 500 kilogram masses. So, what we now know is that the force of gravity is proportional to the first mass. It's also proportional to the second mass, and it's inversely proportional to the square of the separation distance. So that means, remember when we have these, we can multiply them together. The force of gravity is proportional to m1 times m2 times 1 over r squared, which is the product of the masses over the separation distance squared. See how I just multiplied those together? This, of course, makes a wonderful concept builder when he can ask you what happens if we, what happens if we double all of these? Well, we get 2 times because of this mass, another 2 times because of that mass, which makes 4, but we get 2 squared on the bottom, which is 4 over 4, which is 1, which means the force of gravity doesn't change. See how we can do that? We can kind of think through this. And that's going to be something that we're going to do on a concept builder. A lot of proportional thinking in this unit. But of course, what I want to be able to do is to figure out how big is the force of gravity between any two masses that are any distance apart. And for that, we need an equation. And to turn a proportionality into an equation, we need to put in a constant of proportionality, which at this point I'm calling z. Now, we've had some really nice constants over the labs we've done this year. Several times they've been 1 with no units, and so we can just forget they're even there. This one, not so nice. right? Not so nice. So how are we going to figure it out? Well, we're going to compare this general math model to each of our 3 specific math models and see if we can't tease out what z needs to be to make everything work. Here's what I mean. So here's our first math model, right? This is the first part 2 of the lab, right, where we varied the mass 1. And these are the constants we kept. And here's our general math model. Well, I'm going to rewrite our general math model to look more like this one, like so. I just factored the m1 out, right? It's all multiplication and division, so it's commutative and associative. And if you notice, we got the force of gravity's here, the m1's here. That means the slope in the lab has got to be equal to z times m2 over r squared. Yeah? Right? For both of these equations to accurately predict what's going on in the lab, right, the slope we got in the lab has got to be equal to this. But we know what m2 and the separation distance were in this part of the lab. Right? So if we solve for z, multiply by r squared, divide by m2, plug in our givens, we get 6.7 times 10 to the negative 11th Newton meters squared, right? There's a Newton meter squared over kilogram times a kilogram over a kilogram squared. There's our constant. It's not a nice constant, a little hard to remember. It's actually probably in your TI calculator, right, as a saved constant. We'll give it a name in a little bit as well. But this is its value to 2 sig figs. I'm actually going to give it to you to 3 sig figs as it's conventionally known. But in terms of the accuracy of the lab, this is about as far as we could go. So not a nice constant. Got a lot of units we got to keep track of. But it's what nature is telling us will happen. Now, you might not be so surprised to find out that the second part of the lab works exactly the same, because after all, it showed the same relationship with the same slope, right? Here's our second part of the lab. Here's our general math model. Exact same little math here, except we pull m2 out. That means the slope from our lab has got to be equal to z times m1 over r2. Solve, plug in, and not so surprisingly, because you have the exact same constants and the exact same slope, you get the exact same constant of proportionality. Third part, a little more challenging. Here's our general math model, our specific math model for the part 4 of the lab, where we varied the separation distance. And here is our general math model. If I pull out the 1 over r squared out of this, right, this is what I have left. 1 over r squared, force of gravity here, and that means that the slope in our lab has to be z times m1 times m2, which are the 2 things we kept constant in this part of the lab. So, divide both sides by m1 over m2, plug in the 500 kilograms. Notice we get the units we got before, Newton meters squared per kilogram squared, and you probably aren't that surprised to learn we get the exact same constant of proportionality. 6.7 times 10 to the negative 11th Newton meters squared per kilogram squared. So this is a very important constant of proportionality because it allows us then to calculate the force of gravity between any 2 masses any specific distance apart from center to center. Because it's so important, it's given its very own symbol and its very own name. It's called the gravitational constant, and it is denoted by a capital G. This is not gravity. This is the gravitational constant. And here's what it is to 3 sig figs. It's 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. In our simulation, we could go about 2 sig figs, which was 6.7, right? But this is the value that typically is used in a traditional problem. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Now, if you have it in your calculator, you might even have more decimal places. I want you to notice how those units work, right? If you plug those units in here, notice that the kilogram squared on the bottom will cancel out with the kilogram squareds you'll get when you plug in your masses in kilograms. And the meters squared on top will cancel out with the meters squared when you square your separation distance in meters on the bottom, which will leave you with units of newtons, which are force units. So if you ever forget what the units are on this, you can kind of tease them out from the equation. What do the units have to be so that everything cancels out and leaves you with newtons of force of gravity? If we plug that in, we get the force of gravity is equal to the gravitational constant times the product of the masses divided by the separation distance squared. This is what is known as Isaac Newton's law of universal gravitation. Now, it doesn't explain why the force of gravity is this size, but it does allow us to predict the force of gravity acting between any two masses at any separation distance. Separation distance usually measured from center to center of the objects. So this is a very powerful law that allows us to predict some things. And we're going to see over the next few days how this kind of builds into things that are orbiting, which after all, remember, is how Isaac Newton conceptualized this, as the force of gravity maybe is the force that keeps the moon in its orbit around the Earth. We're going to see where does our little g come from that we've been using all year long. Right? Where does that 10 or 9.8 newtons per kilogram gravitational field strength come from? Well, it's actually predicted by this law of universal gravitation. And then we're going to do various other things with it as well, okay? Including quite a bit of proportional thinking.